Hello, welcome. I'll be presenting the talk on In Silico Veritas, Do We Trust Computers? My name is Eric Mueller, and I'm from the Department of Chemical Engineering at Imperial College, London. I was tasked with discussing a little bit on the topic of how much faith do we have in the results from molecular dynamics simulations. It is It is well known that MD or MC or any of these atom-based molecular simulations provides for some very impressive insight on the molecular aspects of matter. We use it frequently and it may be in many cases without any reservation to model biomolecular systems. The 2013 Nobel Prize awarded and the recent COVID news on modeling the virus are classical examples of how important atomistic molecular dynamics or molecular modeling has been. Half a century ago, the big questions were about what are the methods, what are the algorithms, how do we go about doing simulations, how reliable are our methods of solving the statistical mechanical equations. Other problems we had probably half a century ago was the capacity of current computers. Nowadays, the increasing speed and low cost of computings make actually algorithmic advances obsolete. It's just to give an example, Gibbs ensemble was developed to be able to model two phases in equilibrium, trying to avoid the interfacial region, which was, in terms of computing, was costly. Today, it's probably easier just to do a direct two-phase MD simulation with thousands and thousands of atoms. It will be simpler and probably just as effective. So the speed and the size of the computers we have are making an enormous difference in terms of the types of problems that we can explore. So the real question that is missing, or the key question that this talk tries to address, and actually it's a question of the industrial challenge, is how much faith do we have in the results? Since basically we can say that software and hardware issues are things of the past, although no, not completely, because of course we still are advancing these areas. I think these are not the bottlenecks. Everything now boils down to the force field that we imply. And the force field has basically three types of attributes, which sound very similar, but have slight differences, which are important to point out. The first and most obvious is its accuracy. So accuracy is defined as how close the results are to the expected experimental ones. But there's two other sides to this triangle. And the other one is transferability. Basically, can I use parameters which I fit to one atom or one class or one type of molecule? Can I use them in other molecules which in principle are unrelated or unknown? But there's also the problem of representability. Can I use the parameters fitted to a given property, let's say density or interfacial tension, to reproduce other different properties, like, for example, second virial coefficients or, for example, viscosities? And behind everything is the specter of overfitting, which simply will give us some very odd results. And I will show you an example later on. So the first thing I'd like to discuss is representability. I remind you, representability means basically fitting a potential or a force field to one property and then trying to see or trying to believe that it will represent the other types of properties. And a nice example I'd like to show, which is from our own recent research, is the use of the compass force field for modeling interfacial systems which have water. The original compass force field had a water model. It's refit and renamed as the PCFF water model. This water model was originally fitted to the properties of ice and to interfacial properties of water. However, analyzing the PCFF original water model, it provides for a very poor radial distribution function of the oxygens in water, especially in the bulk. To the point in which where you look at the neutron scattering of the OO radial distribution function, and it bears very little resemblance to what we would expect from water with the hydrogen bonds and the overall peaks. So this water model has been reparametrized and refit in what is called now the PCFF plus model. The objective of the oxygen radial distribution function in the bulk has been improved, and the properties like the density have also been looked and studied. And it has been actually used quite for quite some purposes in bulk property of mixtures. We were interested in using this water model along with the rest of the PCF plus force field to study alkyl polyglucosides, APGs. APGs are natural are green surfactants made of a sugar-based head and an alkane tail. They were discovered in the 60s or mentioned in the literature in the 60s, but they haven't been so popular. Their green nature has made them interesting again, and there are interesting applications which are currently being sought. Simulation of a surfactant in, for example, an oil-water interface is reasonably straightforward with current computing power and with current computer software. We can place the surfactants in the middle of a water oil slab. In this case, it's a decane slab. And through these, after equilibrium, we could look at the pressure profiles, obtain the interfacial tension profiles in these systems. So the methodology is reasonably well known, and I think I won't delay any more talking about this in this audience. When we started looking at these systems, we obtained certain results, which they were reasonably correct, looked correct and expected. And we started looking then also at the water-air interface, or the interfacial tension. And when we plot the interfacial tension as a function of the coverage of the surface, or the amount of surfactants at the surface, we ended up with a graph that looks like this one, which immediately raised a series of red flags. This was definitely not what we were expecting. The interfacial tension was, according to our intuition, was supposed to smoothly decay from a value of pure water near 70 dynes, slowly down to the low value corresponding to a critical micelle concentration. Definitely, we did not expect a peak, and we did not expect this overall shape. Looking at the snapshots, again, we did not expect this behavior. There was clustering of the surfactants at the interface, and there was no spreading. We were expecting the surfactant to spread smoothly and homogeneously across the interface. Finally, the interfacial tension that we looked at, the final interfacial tension at the critical micelle concentration was extremely high for this. It was 35 dynes, and basically only implied that there was 10 dynes, with a lowering of only 10 dynes with the addition of surfactant. All of these things yelled that there was something wrong with the model. So we started looking at what went wrong. We had certain confidence that the parameters for the surfactants were okay, and we looked at the modification that had been done to the water model. Basically, it's a fixed charge 3-point site model for water, rather standard, somehow primitive if you want to consider other more sophisticated models. But the thing that stood out very strongly was the fact that the dispersion energy for the oxygen was lowered significantly in the newer model. the PCFF plus model, which we were thinking that is giving wrong. We were thinking that it was an improvement, but now is giving us wrong tensions, has basically a very, very low value of epsilon. This on the right-hand side graph, you see what the two interactions between two water models in terms of these of their potentials, and you can see that the potential well is very, very different from these two water models. Historically, the water model was fitted to provide an overall fit to most relevant properties, but this original model was refitted to provide for better solution or bulk phase properties. And basically, it had been converted into a hard sphere model with charges, removing all the dispersion. But this large and maybe unreasonable dispersion was somehow taking into account in some way the hydrogen bonding environment encountered at the interface of water. So we went back and started using that water model again, the old water model. And guess what? The red line shows the results, completely expected now. It starts from a reasonably correct value for the interfacial tension of pure water. And as we advance and put more surfactants on the interface, they spread homogeneously. There is a slow, continuous lowering of the interfacial tension until we get a reasonably low value. And the area per surfactant from the simulations matches extremely well with the experimentally accessed value. So in hindsight, by putting things right, we parameterized the water model but destroyed the representability of the water. I have another example here that looks a little bit also at transferability and accuracy. And in this case, we had two nitrogen-based compounds which are relevant in the context of CO2 capture. The one on the left, which I'll just call DMI to avoid pronouncing the name, is a molecule for which we have some limited experimental data. And the one on the right is in principle unknown. We performed some experiments on that and obtained some experimental data, but in principle there is no experimental data in the open literature. Again, the simulation was done using the PCF plus force field with rather straightforward simulations to find the density of the system at liquid-like conditions and normal room temperatures. The two molecules were reasonably similar. They're very polar. They have more or less the same groups. So we should expect a reasonably same behavior in both of them. But the results show very differently. The known one, here in this plot, we have the density as a function of pressure. The simulation results are open symbols, and the closed symbols are the experimental ones. We see that for the known compound, DMIA, we have a reasonably good fit between the experimental data and the simulations. But for the HEI, which was the unknown compound, which now we tested against our experiments, we see a 2% error, a systematic 2% error. Now, this is 2% error is borderline of unexpected. One would expect much better agreement for a fully atomistic force field. So again, by overfitting existing groups, which was basically what happened with DMI, we lost the transferability of the model. So again, the specter of overfitting is in that corner, getting us worried. So just as a conclusion, I just wanted to show that these are two day-to-day examples which show how we routinely perform calculations of complex mixtures, but are still pressed with the question of what is the accuracy, what is the transferability and representability of the results. In these two cases, we knew the answer, but what if that was not the case? And what about the other demons that are looking around, metastability, long relaxation times, long-range corrections, quantum effects, reactions, et cetera, et cetera. So basically, my conclusion is that there is still a long way to go for activities like the Industrial Fluid Properties Simulation Challenge, which I applaud. And there's still much we need to learn about this issue. And I'd like to end with two slides, one from Professor Prauschnitz and a quote from his thermal book. And never take the results from a machine for granted. The virtue of a computer is its speed, not its intelligence. And he wrote this over 40 years ago, but it's still very much true. And I'd like to end with acknowledgments of the people who have contributed to this talk. Thank you very much.